And number 49 was very similar to the operations that are up here. There are multiple operations that you can do with a limit. The first one has you taking the limit as x approaches 5, and then 3 times some function. I don't know what that function is, and it actually doesn't matter what the function is, because all you need to know is that it's going to be equal to the limit of the function times 3. So whatever the limit is of the function, if it's 5, I would take 5 times 3. So in question 49, I think it was asking for the limit of, but I had it memorized and it's vanished from my brain. So the limit of negative 2g of x. G of x is 8. So you're taking 8 times negative 2, which is negative 16. So you're taking the limit, you're multiplying it by 3, whatever the limit of the function is. So it's really the operation of the limit, not the operation of the function. So for the second one, we have the limit of as x approaches 5 plus of f of x plus or minus g of x. So really, you're going to take the limit of f of x, separate it, do the limit of g of x, and either add or subtract those values. So if my limit was L and my other limit was K, I would add the two numbers together or subtract the two limits. So you're not physically adding the functions together and creating a new function. You're taking the limit of the first function plus the limit of the second. And I think that was number 49, part B. So the limit of the first function plus the limit of the second function. You're just adding the limits together. So operations of functions, you're actually focusing on the limit. You're not actually adding the function and creating a new function. Number 3 is the multiplication one, where it says you're multiplying two functions together. Well, that could be the hard way to do it, but instead you could do the same thing that we did to number 2. So take the limit as x approaches 5, 10, 15, 20, whatever it happens to be, of f of x times, separately, the limit as x approaches 5 of g of x. So essentially you're taking the limit of the first one times the limit of the second one. So again, you're not multiplying the functions together and getting a new function, you're multiplying the limits together. So if I had the limit of f of x times the limit of g of x, like for number 49, you would multiply the two limits together. So part C of number 49 wanted you to divide f of x by g of x. So you're dividing the two limits. And then the last operation is when it's raised to a power. So then you're just taking the limit and raising the limit to the power. So essentially, you're not doing anything to the function. You're applying the operation to the limit. So that's how you would do operations with limits. It's really applied to the limit, not the actual function itself. So the function could be any type of function. As long as you're getting the limit of that function and applying the operations to the limits, that would be how we would evaluate them. So it's actually easier. Because if I had two crazy functions and I was trying to add them together, it would be a lot harder to add them together than just looking at the limit of those functions separately. Questions? So again, number 49 in your homework, you were to use the limits and do the operations just on the limits. Questions? So today we're going to look at really 4 different ways to evaluate a limit. We've done it graphically and by direct substitution. So your homework last night was graphically using a table of values. Direct substitution was like the one that Aaron did, that last group of problems for direct substitution. So we're going to look at other algebraic ways that we can also evaluate limits today. And that would just be flipping to look at the next page. The magic box.
It was worse on the other side of the room when we used to sit over there.
Was it worse on the other side of the room? Yeah. Definitely. So if you look at page 7, it talks first about the limit of a polynomial. And that's the first problem we did yesterday was a line. Polynomial is continuous. It has no breaks. It has no stops. It has no holes. A line is a polynomial. A parabola is a polynomial. Anything with a positive power exponent is a polynomial. Polynomials use direct substitution. So you can take the value you're trying to find the limit of, directly plug that in, evaluate, and then out pops your limit. So Katie, if we have the limit as x approaches negative 1 of x squared plus x minus 6, what would you do to find the limit?
Put in -1, correct?
Yeah, so you place -1 in for x, which is something we've already done. That would be like evaluating the function. Now I just have this limit notation. So once you plug it in for x, you lose the limit notation because you're using the number in place of x. The value x is supposed to be approaching. So Katie, -1 squared plus -1 minus 6 is -6. That's the limit, which is really the y value of the function. They mean the same thing. We're just thinking about it in different terms now. So now I'm thinking about if I was looking at this graphically, the graph is approaching this number from the left and the right, instead of it just being a point. Now it's approaching the value from the left and the right. Example number 2 underneath. Actually, I guess it's way number 1, outside of the direct substitution. It says other ways of evaluating limits. The first way is to factor, which is the second one that we looked at yesterday. So we have the limit as x approaches -3 of x squared plus x minus 6. Same problem up above. Except on the bottom, we're now dividing this by x plus 3. Why doesn't direct substitution work for this problem? David?
Well, when you put a negative 3 on the bottom, you get a number this area.
Yeah, so if you put a -3 in the denominator, you're going to be dividing by 0. So it's not going to work with direct substitution. It's also not a polynomial, so that's why it doesn't work. So instead it says to factor, because that's an algebraic method that we can use to alter the appearance. So David, how would you factor the numerator?
X plus 3, x minus 2.
Right, x plus 3, x minus 2. So if you can alter the appearance of your original equation, your original function, then we want to try and do that. Because when we factor, we get the denominator to cancel out. So what you have left is a continuous function in appearance. And you'll look at it in the calculator. So now you can substitute the -3 in. And David, when you substitute the -3 in, the limit is -5. So again, that would be the limit. Is this limit reached? No. Anytime you have a part that cancels from the function, it is not reached. Because when it cancels, it creates the hole in the graph, and literally it like wipes out that point. So that point doesn't exist anymore because we've eliminated it from the function, so you eliminate it from the graph. So direct substitution, that point will always exist, the limit will always be reached. If you alter the appearance and you cancel a part out, then the limit is never reached. So it's not going to get to that exact point, it just gets really close to it. Any questions? So the one at the bottom is going to be the new one, the one that's a little different. Except we've done rationalizing in trig, we did rationalizing in pre-calc, we've done a lot of rationalizing. What does it usually mean when you rationalize? Anna?
Is to take a square root out of the denominator.
Yeah, usually we do it to take a square root out of the denominator, which is why we did it a lot in trig. We took square roots out of the denominator to simplify. However, there's not a square root in the denominator. It's in the numerator. But can you plug a 0 into the denominator there for x? No. So unfortunately we're not cool. Still got to figure out how to solve the problem. So our goal is to take whatever the limit is approaching and plug that in for x. Well, if we do that, if I plug a 0 in for x, I end up with the square root of 1, which is 1. Minus 1 becomes 0, divided by 0. So now I have that 0 divided by 0 thing. So we have to figure out a different way to solve the problem, which is why we're still going to rationalize, but we're going to be working with the top of the function instead of the bottom. What does it mean to rationalize, Hannah?
She's like, why'd you call me?
Uh-oh, I shouldn't call on her. She has no voice, apparently.
Oh no.
Like, what would you do to rationalize? How would you usually, what method would you usually use to rationalize?
Well, usually if we had a square root on the bottom, usually we'd multiply the bottom by the square root. So if like we had the x plus 1, like the x plus 1 under the radical on the bottom, usually you would multiply both the numerator and the denominator by that term to get it to cancel out.
Right, usually we multiply by the conjugate to get it out of the denominator. Remember in trig, we multiplied by conjugates to get it in like a Pythagorean identity form? It didn't always have to be in the denominator either. What would I multiply by? I have the square root of x plus 1 there, but that's not it. What do you multiply by? What's the conjugate of what's in the numerator?
Be the negative square root of x plus 1.
So close.
Would you add one just have doing the minus one?
Right. So the conjugate is the part that changes the middle sign. The terms are the same, but the middle sign, a conjugate is having a plus and a minus. So I have the same terms, but one plus and one minus. So when we multiply by conjugates, the goal of using the conjugate is to hopefully get something to cancel, or in trig terms, we use conjugates so that we could then get an identity to use. Aaron.
We multiply the denominator by anything.
You do, because whatever you do to the numerator, you have to do the exact same thing to the denominator to keep the fraction equivalent. So if I multiply the top by 2, I have to multiply the bottom by 2. So if I'm multiplying the top by the conjugate, we have to multiply the bottom by the conjugate. That keeps it equivalent, just like equations, fractions kind of work the same way. So we are going to see if we can do a little multiplying here. When you're multiplying the square root of x plus 1 times the square root of x plus 1, what's that become? Katie, what's that become? Square root of x plus 1 times the square root of x plus 1. That's just x plus 1 because they cancel. You have the same square root that you're multiplying. With conjugates, what happens when you multiply the middle two terms? They cancel. So don't write them down. Every time they're going to cancel. That's what happens with conjugates. So I have a positive square root of x plus 1. I have a negative square root of x plus 1. They're going to cancel. And then finally, we have negative 1 times positive 1, which is just minus 1. All right, so then we got to look at the denominator. When we did trig problems, we always multiplied the one part together so that we then had the trig identity. But the other part we always left in factored form because our goal is to get something to cancel. And the way things cancel is when they're left as factors. So I'm going to leave the bottom as a factored form with the x outside, and then the square root of x plus 1 still in parentheses. Because our end goal is to get that denominator not to be a 0. And that means I have to get rid of the x because that's the part that's making the denominator 0. So Marie, what happens with the top of this fraction?
The ones cancel.
The 1's cancel. 1 minus 1 is 0. So we're just left with x. On the bottom, here's that little x guy sitting out front, multiplied by the square root of x plus 1, and then plus 1. So Marie, what do you think would happen?
The x's would cancel considering that you could do that.
Yeah. So now, because we left it in factored form, we get that part to cancel. The part that was making the denominator 0 is gone. So we've altered the appearance by rationalizing it, but we really rationalized the numerator this time. So the numerator has a 1. The denominator has that square root, which pretty much most of the year we said you couldn't have a square root in the denominator. But now we need it there because we had to get the stuff out of the numerator for it to work. So this is as far as we can go algebraically. We've altered the appearance by rationalizing. What's the last step that we have to do to actually evaluate the limit? David?
You plug in the 0?
Yeah, you plug in the 0. So now I can take this 0 and plug it in for x. And David, when you plug it in for x, you end up with 1 divided by 2. But we couldn't plug it in for x in the original equation because it made it divided by 0. So whatever makes it 0 is the part that you have to try and get rid of. That's the part we're trying to take out of the equation. So rationalizing is a method that you can use to eliminate a part of the fraction that's making it 0.
So is that not reached?
Exactly. So again, this is not reached because we still canceled a part out. Any part that cancels takes a piece out of the equation and it creates that hole in the graph. So this one is not reached because that piece canceled the x term. Questions? So that was the big algebra problem. We have one more to do, but we're going to look at a couple of graphs so that we can look at what's going on graphically as well, because sometimes, unfortunately for me, a calculator is the only way to solve a problem that we can do right now, because you just don't have quite the math that you need till you get to next year. So if you look at this function, we're going to plug this in the calculator. We have the limit as x approaches 0 of the sine of x divided by x. Again, we're dividing by x, so if I plug a 0 in there, I'm dividing by 0. The sine of 0 is also 0, so I still have that 0 divided by 0 form. So plug it in your calculator, because we don't really know any other way to solve it using algebra or trig. Like, it's just kind of relying on technology every once in a while. And hit the graph button. And you should get a little mound. Try yourself a little sketch. So we have this mound that's going underneath the x-axis, but it's actually just like skimming along the x-axis underneath of it. It crosses over it, and then it kind of reaches a max value. So skimming along underneath the x-axis, crossing over the x, going back, and then skimming along. Something similar to that. Mine isn't quite symmetrical, but let's see.
Mine said invalid dimension.
Uh-oh. What's in this graph that your calculator really isn't showing you?
Someone used my calculator at lunch, but I don't know what they did.
Oh, maybe they turned the clock on. There you go. So there's one part in this graph that the calculator isn't showing you. That needs to be in the graph. What's happening at x equals 0?
Oh, there's not going to be.
Yeah, there's not going to be a little point right here. That's an open circle. Because you can't divide by 0. So that means that's going to be undefined there. There's a little open circle sitting there. So the question is asking you to determine the limit as x approaches 0. Which means, using my little pointer fingers from the left and the right, as I'm going in towards 0, what's the y value of the graph doing? Going up to 1. Is the limit reached, Marie? No. But it's still getting really close to 1. So it still has a limit. Questions with that? So it's undefined at 0, which is why there's a little hole in the graph. But as you're moving along that graph and kind of curving up, your pointer fingers are meeting at the same y value. So therefore there is a limit. It's getting really close to the y value of the button. Any questions? So I'm going to skip the 2 graphs for now. We're going to come back to them in 5 minutes. I'll say 5 minutes. I'm going to do one other algebra problem yet. And that's on the next page. And then we'll look at those other 2 graphs. So if you go down to where it says, like, it's the next page, it says a limit from calculus. And look at number 3. I want to do, actually, I think you have number 6. I have number 3. I don't know why it says 6. I feel like it should say 3. There we go. So the last problem, essentially, at the bottom of your page. Anybody recognize this?
Well, that's the
Oh, yeah, what is it?
answer. It was the first thing we learned.
It is. It's the first thing we learned that was like truly pre-calc material. This guy right here was the first thing that we
I
did.
couldn't tell you.
I remember this, but I don't remember what it was called.
What chapter was that?
I do not even remember seeing this.
You don't even remember seeing it? We did it a couple of times in chapter 1 and 2, I think.
Dairy
One-
Queens.
Look at section 1.1, 1.3, 1.4. DQ, Dairy Queen. Let's all go to Dairy Queen.
I love it.
Difference quotient. Did Ethan say it and I didn't hear him?
Like, under his breath.
Under
though,
his
that
breath,
literally
because
allows the
David
other
can hear you.
person-
Can Kyle vouch or Kyle didn't even hear?
Classmates here.
Oh,
It was like
yeah,
couple out and get one.
So the difference quotient essentially was a way for us to evaluate functions. We didn't really do much with it at the beginning of the year besides work through it like algebraically. We are going to start pulling this back and you're going to see how this relates to graphs. So eventually we'll see next week how it relates to graphs. Not quite yet, but we'll get there. But we're now going to apply the limit part to it. So this would be like the new part that we're going to apply after we do the algebra part. Does anybody remember how it works? So you start with the f of x plus h.
When you plug in just
You
zero.
plug in the x plus h into the other equation.
Exactly. So we're not going to do the zero part yet. David's like, I really don't remember this.
Because it was like the f
This
of
is
x, so you're
honestly
putting
like-
in.
This is
not
like-
reading, anything in my head.
So we're going to take whatever's in parentheses and plug it into the function replacing x. So instead of x squared, I have x plus h. Instead of minus 2x, we have minus 2 times x plus h. So you're taking the stuff in the fraction and going into the function. And then the next part says minus 2 times, sorry, I already did that part. Let me start over. The next part says subtract f of x. So we're going to subtract whatever's represented by f of x equation. Well, what's the equation that represents f of x? Yeah, x squared minus 2x. All of this is divided by h. You can't plug a 0 in because then you're dividing by 0. So I can't do anything with the limit until we do some algebra. So FOIL, distribute, cancel. This piece here gets FOILed. That's x squared. I'm really multiplying x plus h times x plus h. 2xh, because there are 2 of them. And then h squared. Distribute the negative 2 through. Distribute the negative through.
We have cancellation.
You should have a whole bunch of things, or at least a group of terms that cancel. Which is what always happened with all the problems that we did. So x squareds, positive and negative. 2x, positive and negative. And if you look at the 3 things that remain, David, what do they all have in common?
They all got an H.
They all have an h, so I'm going to pull that h out. 2x plus h minus 2.
Can they cancel or?
Yeah, they can cancel. So the whole goal is for us to be able to plug a 0 in for h. Well, we can't plug a 0 in until we get that h to cancel. So because all the terms have an h in common, if you factor that h out, then that h in the denominator cancels. So you are left with 2x plus h minus 2. Can you plug the h in now?
Yeah.
Yeah. When you plug that h in of 0, what do you have? 2x minus 2. This is going to be an equation that represents something for us. In a little bit. Just not quite yet. Got to do a little bit more with limits. That's the difference quotient. Questions, Jared, are you alright?
Yeah.
He says, why did I take honors pre-calc because you really wanted to have Mrs. Kane again. Just a sleepy Tuesday. Every day is a sleepy day for you, Jared.
Tuesday's the worst day of the week.
Yeah, I don't know. I think Wednesdays are kind of rough.
Mondays
are the worst.
Let's be honest, every day that's
Wednesday
not
you can-
Friday is kind of rough.
Yeah.
Wednesday you can say
Nobody
like, alright,
remembers.
at least we're over halfway there.
Okay.
Wednesday morning is rough. Wednesday
Afternoon is okay. All right, so I'm gonna have you flip backwards now. I apologize for making you flip. See, I'm keeping Jared awake, making sure he's flipping his packet back and forth, trying to keep him awake over there. The last thing that we're going to look at today is something called a one-sided limit. Did you know numbers actually have two sides?
Front and back.
They have front and back. They have a left and a right. So there's a left side of a number, which means you're on the negative side. There's a right side of the number, which means you're on the positive side. We approach a limit from the left and to the right, and they're supposed to meet in the middle. So you will look here at the notation and see a little negative sign after the number. Do you do that in chemistry too, where you have like a positive or a negative?
That's how you write.
That's
That's how you tell the charges.
Okay, right. So when it's after the number. So now for us, when it's after the number, it represents the left side if it's negative, the right side if it's positive. In your calculator, I'd like you to plug in this equation. The limit as x approaches 0, you're not plugging in, but you're plugging in the absolute value of 2x, which you have to hit the math button to get absolute value, divided by x. And make yourself a little graph. So anytime you're looking at a graph, draw the graph as your work, because there really isn't any other work. And we're going to look at the left side of 0 and the right side of 0.
Oh,
This is kind of a different graph.
That's weird.
interesting.
All right, what'd you get? Hopefully. 2 lines. David, the line on the left, what number does that go to? 0? What's the y value that it goes to?
-2.
Okay, so the line on the left goes to 0, -2. Is it going to be an open circle or a closed circle? Open, yeah, it's going to be open because I can't divide by 0. So you have this line coming in on the left. That's called your left-sided limit. What is the limit of the line that comes in on the left side? What's the y value that it goes to? -2. So our left-sided limit is -2. That's the left side of the graph. Looking at the right side of the graph, where's that line at?
2.
2, up at 2, still at 0, open circle because it's still undefined, and then it goes to the right. So what's the right-sided limit? +2. Are they the same? No. So would this graph have a limit at 0? No. We actually did this problem yesterday, but we didn't really think of it as a left and a right side. We just said that the little fingers need to meet at the same number. The reason a limit doesn't exist is because the left and the right side don't meet at the same number. David.
So if you have no limit at 0, well, for this graph, would there never be a limit for this graph at
Ever.
even if you said as x approaches like 3 or anything?
Well, we could do it at x approaches 3, because 1, 2, 3, right here. Because I'm just using this piece of the graph that is involved. Yeah.
And you just ignore that.
You can just ignore that. So on Thursday and Friday of this week, we'll really be looking at graphs, and you'll see that you're allowed to only look at a piece of the graph and ignore the rest, because you're really focusing on whatever this number is. Like that number is the focus that you're looking on in the graph, looking at in the graph. Questions? I wanted to graph the last piecewise function. I don't know if I'll get a chance. We'll see.
That looks like a lot.
It does look like a lot. I don't know if we have enough time to try and make it work. Plus 4x. I'm going to draw a little dashed line at 1 so that I know where x is 1, because that's not a very straight line, but here's a little straighter. So the first equation really says -x plus 4. It's a line up at 4. 1, 2, 3, 4. Its slope is down 1, right 1, which makes my x value. But it says x is less than 1, so I put an open circle. Which way would you continue the line if it's less than? Is less than left or is less than right? Left. So from my open circle at the x value of 1, I'm making a line going up to the left. So whatever your x value is, I'm just putting a dashed line there because that's where everything is focusing on. So I'm going left. The second one I plug into your calculator. So go to y equals, plug in -x squared plus 4. go to the table of values and plot some points from the table of values starting at 1 for x. So start at the x value of 1. The reason we're using 1 is because there's a 1 in my restriction. So if the x value is 1, the y value is
1. Oh, wait, 3.
3. If the x value is 2, the y value is
0.
4.
I got
Yeah.
0.
I got 4.
I got 0.
Did you put a negative in front with the x squared plus 4x?
Yes. Oh, didn't put an x after 4.
Okay. If the x value is 3, the y value is 3. If the x value is 4, the y value is 0. Okay, there's my 0.
What?
So it kind of is like a little piece of a parabola that pumps up and goes back down. So at the x value of 1, do they both meet at the same y value? Yes. Since they both meet at the same y value, then the limit is that y value of 3. So in this case, they're both meeting at that same value. Karen, sorry.
It isn't.
It isn't reached.
Even
Yeah,
though
you
they're
guys
not
are good.
touching- Wait. They're not touching, but there is a limit.